Hello folks, and welcome to part 1 of the 24th lecture in our Probability and Statistics course. This will be our final lecture, and for today's lecture we are going to be discussing a slightly more advanced topic when it comes to statistical hypothesis testing. We're going to be discussing the testing for a difference in mean for two normal populations. So here we're going to have two normally distributed populations, and we want to test whether or not we believe they have the same mean, or is there a difference in the means of these two populations. So as an example to lead in here, let's think about recovery time from COVID-19, and let's assume that recovery time is normally distributed. So X is going to be the amount of time here it takes a person to recover from this disease, and we assume it's a normal random variable, let's say with mean 14 with unit of days, so 14-day mean recovery time, and the variance of recovery time can be 4 days here. So there is a population. We have such a random variable. We can use this random variable to create a population by taking a countably infinite collection of copies, independent copies of our original random variable. So x1 is going to be a normal of this type, x2, and so forth. This represents the recovery time of the first person who catches the disease, the recovery time of the second person, and so forth. Now we can suppose that we have developed a treatment method, and we are going to have the people who are treated with this new method are going to have a different distribution for their recovery time. So we're going to assume that it's still normal, the recovery time for people who receive this treatment, but it is a different normal than it was before. So it's going to have a different mean and a different variance potentially. And we're hoping that the recovery time for people who have received this treatment is going to be smaller than the recovery time for people who have not. So mu2 here would be the average recovery time for people who receive our new treatment, and mu1 is the average recovery time for people who go without this treatment. And we know that to be 14, we are assuming. We're hoping that the new mean recovery time is less. So we could come up with an alternative and a null hypothesis, and they might look something like this. So H0's going to assert that the new recovery time, average recovery time, is the same as the old average recovery time. And our alternative hypothesis will assert that they are not the same. It's actually fairly common for the null hypothesis to be a result that you don't believe, that you're hoping to reject the null hypothesis when the observations that you've made would be too unlikely under the assumptions of the null hypothesis, meaning your p-values are so small that you reject the null hypothesis. It's very common that investigators frame things this way. It's irrelevant which one you initially assume versus which you do not, but this is sort of a standard formulation. So we're hoping that mu2 is less, but our null hypothesis asserts that they're the same. It would very much be appropriate here to take your alternative hypothesis to be one-sided, to just be that mu2 is strictly less than mu1, because that's the result that you're hoping to actually be able to demonstrate here. But as we've said, we're not considering one-sided alternative hypotheses in this course, just so we can lay out the basics for the simpler case of the two-sided tests. So H1 here for us will simply be that they're not equal, though in practice it would make a great deal of sense in this context to have a one-sided alternative hypothesis of the form shown 3 lines up from the bottom here. Alright, so how do we actually test this? The core of the work is going to be done by this theorem, which gives us our new test statistic, which is going to be a standard normal here for these two normal populations. So this theorem is going to delineate for us what the test statistic is going to be for tests of this type. So if you have a normal population, x1, x2, and so forth, and you've got the population mean and the population variance for that population, and you have a sample of size n1 drawn from that population. So here in bullet point 2, we do have a sample drawn from our initial population, from our first population, and the size of this sample is n sub 1, as shown here. And then we have an entirely new normal population, so we're going to designate these with y's instead of x's. And there is a countably infinite population of these. They have their own population mean and variance, and these numbers could be the same or different from what we had for the first population. And we have a sample drawn from this second normal population as well, and it need not be a sample having the same sample size. So the sample size for this second sample is n sub 2 for this sample of y random variables. So we've got a sample from the first population of size n sub 1, and we've got a sample from the second population of size n sub 2. With these two samples taken from these two normal populations, we can form this statistic. So this is a random variable defined in terms of here are two samples really, one taken from the first population and one taken from the second, but we can find the sample mean for that sample taken from the first population, we can find the sample mean for that sample taken from the second population, we can take the difference in the two population means here and divide by this expression, which is going to be the sum of the two corresponding expressions. Well, that's not quite exactly right, but this expression here, given in terms of the population mean for the first population divided by the sample size for the sample associated with that population, plus a similar term for the second population, all under the root together. So note that it is the square root of the sum of these two terms. And now, if your null hypothesis is true, so that mu1 does equal mu2 here, they have the same mean, this expression is going to be 0 in the top right here. And so this whole thing, well, it's worth noting that if your null hypothesis is, in general, you expect this expression to show up near 0, because this whole expression is a standard normal. So we know how to compute probabilities for standard normals. If this whole thing is a standard normal, we can compute the probability of it showing up in different regions. And that's what's going to allow us to compute things like p-values here. So if it is true that these two have the same population mean, these two populations have the same population mean, this mu1 versus mu2 expression here is going to be 0. We're going to be able to calculate the difference in the sample means. We're going to be able to divide by this expression. That's going to give us a number. If that number shows up near 0, then the null hypothesis is believable. If that number shows up far away from 0, then we reject the null hypothesis in favor of the alternative hypothesis. That's the overview of how this is going to work. So statistical testing for a difference in means with these normal populations, we're only dealing with the case where we already have normal populations here, so there's no need to use the central limit theorem. Things are already normal and they remain normal as we modify our expressions. Going from the random variables themselves to their sample mean, going from their sample mean to the appropriate test statistic, no approximations are made in those steps for the case where your populations are normal to begin with. So, if you're starting with these null and alternative hypotheses, so asserting the quality of the means versus the inequality of the means, then your test statistic is going to look like this. And here I've taken the mu1 first minus mu0 to be 0. You decide your significance level in the usual way. Think about a type 1 error and what that means. Think about a type 2 error and what that means. Decide on your significance level. You go out and gather your data. You compute the value of your test statistic shown in the box above, and you find your p-value and draw conclusions. Alternatively, you could perform this procedure with finding acceptance regions. So before you gather your data, once you've set your alpha value, you could, treating this as z, the standard normal, find your acceptance regions for this test statistic ahead of time, and then just compute its value and see if it lays in the acceptance region. We're formulating this here instead of p-values, instead using p-values, where you never find an acceptance region. Instead, you just compute your p-value and compare that to alpha. But then that should lead us to question, how do we find p-values here? And in fact, theoretically, it's going to work exactly the same as every other p-value that we've dealt with. It's the fact that this expression is a standard normal that's going to allow us to compute the probabilities of these tails. If you remember, p-values are defined in terms of the likelihood of seeing an event at least as extreme as the one just observed. So we take our first sample from our first population, we take our second sample from our second population, we compute those sample means, we take the difference, We're assuming we know the population variances, and clearly we know the sample sizes. We compute all of this. That should be a standard normal random variable, and we get some numerical value based on the samples that we actually draw. So this is a number, is little z hat here. And now our p-value is going to be the probability that a standard normal of this type falls further from 0 than the value just observed. So either to the right of its absolute value or to the left of the negative of its absolute value. And this is going to be a left tail plus the area of a right tail. We get twice the area of one of the tails. And I'm going to write it as phi of the opposite of the absolute value of z hat. People will also write this as 1 minus phi of the absolute value of z hat. That's true as well. They're finding the area of a right tail, so they don't have to put in this minus absolute value business. I'm using that instead of doing the 1 minus phi trick, so either one works. And so that's how you find a p-value. So let's do an example here. So suppose we're going to study this recovery time of patients with COVID-19, as we discussed at the beginning of the lecture. We take alpha to be the industry standard of 0.05. So we're taking a significance level of 5%. Suppose that 75 patients that we observe are going to receive no treatment, and we measure their recovery times. So there's a population of all the people who could ever be infected and receive no treatment. We take 75 of those people as our sample, and suppose we know the variance of this first population to be 4, as we stated at the beginning of the lecture. And we find an average recovery time for this 75 person sample, and we find it to be 14.1 days. Our next population is going to be made up of people who actually received this new treatment we've been studying. And suppose we managed to test 60 such patients. So we had 75 patients who received no treatment, and we're going to have 60 patients who receive treatment. Generally, you want the sample sizes to be comparable to one another. You're going to get better results if they are similar. We're not going to talk about the details of that too much, but it's not unreasonable for them to differ a bit in general. So we got 60 patients who receive our new treatment. There is a population associated with. It could be all the people that could ever have the disease and receive this treatment. We take 60 of those. Suppose we know the population variance to be 3.6, not a reasonable assumption, but a close enough one for now. And we measure the average recovery time for this sample to be 13.3 days. I had it at 11.2. After I ran the numbers, I decided to change it to be a little bit closer. So it's at 13.3 days. So, with 13.3 days as the average recovery time here, it is less than the 14.1 that was seen for the sample from the first population, but is it a statistically significant difference? It certainly looks less, but could that just be random, or is it likely that it's due to there actually being a difference in the means for these two populations? So we're going to test the hypothesis that the means are the same, and we sort of hope that we end up rejecting it. We want to know what really is true, but it would be nice if we had a treatment that was working. So our test statistic is going to be the difference between the sample means divided by this square root expression. I've got my population mean for my first population divided by the sample size taken from that population. Likewise for the second, we've got the population variance divided by the sample size associated with that second population. And the numerator is the difference in our sample means. We compute this value to be 2.38, and our p-value is going to be twice phi of negative 2.38, which I then grab my chart, I look up phi of negative 2.38, I get to this value, 0.0086 and change, and twice that has given me a 1.7% p-value. So if it is true that they actually have the same mean, these two populations, those who did receive no medication and those who received medication, if the mean recovery time for those two populations is the same, there would only be a 1.7% chance to see a result as extreme as the one just observed. That is a low p-value, and this causes us to reject the null hypothesis in favor of the alternative hypothesis. So it's looking like our medication is actually doing something. It doesn't look like the mean recovery time for the two populations is exactly the same. It looks like there is a difference between them, which means presumably the mean population time for our medicated population is actually lower than it was for the untreated population. And so that's excellent. Again, we would really have an alternative hypothesis here that would be a one-sided alternative hypothesis that would assert that mu2 was less than mu1. But for this example, we did see what looked like a statistically significant difference in the means for these two populations. So part of this discussion today is summed up in this theorem, where we have this as a test statistic, and in fact we have the distribution of this test statistic, also known as the test distribution, or the statistic distribution. The sampling distribution, I believe it's called, in fact. It's not vocabulary that we have to know in the class. But this is your test statistic. You're able to compute these two things. We're assuming that we know the other things, in the denominator here, and the null hypothesis asserts that this value should be 0. With this being z, we're able to compute p-values in this way. So knowing that this expression is a standard normal, computing our p-values is just a question of computing probabilities for a standard normal, which we do in terms of phi. And that leads us to a slightly modified version of our flowchart for running statistical tests of hypotheses of this sort. Alright, so that will just be it for an overview of the theory for the test for a difference in the means of two populations. In the last part of today's lecture, we'll do several examples and sample problems for these ideas. Thank you, folks. Talk to you again shortly.